Right, so about the differentiability on the topic as on its own, it just happened. We know this already. Most of the times we've seen this one before, where we have dy dx and stuff, right? Where we have changing y, changing x, right? And then we know this one. It's the same thing when we write it this way, okay? Remember initially I was like, when we write something like, let's say f of x, we know it to be y, right? Because you are seeing that this y is actually a function of this x. So if I write it this way, f of x not here, it's the same as saying something like y not but it's just like a different value, a different x, a different y. That's not known, that's what it means. So whenever we try to write it this way, when we write it this way, it's the same thing that we are saying. This whole thing here is the dy dx, which is the slope that we know so far. Okay. But then there's something that we must make clear, right? Let me write this out. When we see what's the name? Continuity. Right? And then we say differentiability. And then limits, right? These three concepts are actually interconnected. Are you okay? So that's why I was like, before you do anything with differentiation, you must be able to appreciate the limit and then the continuity. Okay. So now we are in differentiability. Now we are this side. What it's saying is that before we can find the derivative at a particular point, which is this not here, it's the same as finding the limit as this, the x is approaching this, which is the same as this whole thing here, which is the slope. Are you okay? But it's actually the limit. So we actually define the differentiation rules from limits. Okay. It's through limit that we are able to know most of the fundamental differentiation. So that's what everything that we've written here so far. That's what it says. Right? Because in order to find the derivative of a function let's say this one, f of x, as it's approaching this, is the same as find the limit as the x is approaching. It's like the x inside is approaching this x not here, right? So that's actually the derivative of the function, right? This way. So when we write any function f and I put a dash at the top here, it's actually the derivative of that function, right? So let's say this is the function. It could be anything. The letter doesn't matter. That is just the dash at the top that differentiates them. So if I write something like, let's say d of, let's say, x, right? This is the function. I put a dash here. It's still the derivative of the function. Even if I write something, let's say k of, let's say, y, it could be written anyway. So far as I put this dash here, meaning it's a derivative of that function. Are you okay? And now we come here. So when we started, we got to revise on something that we know that when we write this thing, dy dx this way, we're actually saying the slope, right? If we write changing y, let's say y1 minus y2 or something, right? x2 minus x1 or something. This actually, all these are slope, right? Slope. And then they are saying, say, what if, and then you remember that we got to a point where, like, before we even find the differentiation, we said that we can use the limit to find the differentiation. So we said this is the change, this is the y, and one y, another y, one x, another x. So it's like changing y over changing x, right? So everything here is a matter of changing y and changing x, right? So if it is that way, you are saying, so what if this x, this is the x, right, approaching this value here, the difference between them is very small, right? So let me write this one out. You have this, you know this to be the slope, right? Minus f x naught all over x minus x naught, right? What if the difference between this x and this x naught here is very small, and then we represent the difference between them, which is very small, to be h? So this is what we can do. So clearly we can write that this down here to be h, right? Because we are saying that this is the difference between them, this x naught. We are saying this is the difference between them. We are saying that the difference between them is very small, which is the h. So wherever we see this x here, we can represent it by writing something, right? Because this one is the bigger value and this one is the smaller value. We are seeing the difference between them is very small. So we can write it this way, f, and then we have x naught plus h, right? And then minus f of x naught. That's what everything that we're writing here means. It's just the same thing that we're writing different way. So now, a differentiation, right? We are saying that when it's written this way, let me zoom in. When we write everything this way, right, we understand that when the dash is here, it means that we are doing the differentiation, and this one is the x naught, right? This one x approaching x naught. This is what we know. But what if we bring a dash at the top here? What is trying to say that we are doing the same differentiation, but this time we are approaching the same value from the left side, because just remember this. Let's go back. Let's say we have the number line, right? If this were to be the number line and 0 is here, all this side positive, right? And all this side here will be negated numbers, right? So that's what it means, that whenever we do something like this, or you see something written this way, it's the same thing, but we are approaching the same value from the left side, right? Here we are approaching the same value from the right side because a positive here. I think I should make this clear. This positive up here are not supposed to be there. Let me write it out. These ones. These ones are not supposed to be there. It's supposed to appear only on the side, because we are talking about, it's like the same function we're talking about, so this one shouldn't come. I was to make it look different. But this negative and positive here are just saying that we are approaching the same value from different directions, right? That's what it's saying. So when we are approaching from the left side, we say the left derivative. When it's approaching from the right side, which is this positive sign, we say this one here, we say is the right derivative, right? Because we are approaching the same value from the right hand side, right? Here, whatever the discussion we are doing here, we are doing it on real numbers. That's why this from the left hand side and right hand side they exist. Now differentiation. A function is said to be differentiable at a point if the limit, or if the derivative of that function at that point exists. Right. So let's go over this. Remember initially I was like limit, continuity, and differentiation. Differentiability, they are similar, right? So now they are saying that the function is said to be differentiable at the point this x naught if the derivative of the function at that point exists. And we know that whenever we do this way, let's say we have a function this way, and then it writes it this way, it's the same as when we write what? It's actually not. It's the same as when we write this x minus x naught all over this actually f, right? X minus x naught, right? Which is the same as y minus y naught all on x minus x naught, which is the same as slope, right? So we are seeing say a function is differentiable at a point. These are just the word side, but to get to a point where we do the calculation and stuff. So the function is differentiable at that point when the derivative of the function at that point exists, or when the slope exists, right? So that's what we're seeing here. A function is differentiable in an interval. If it is differentiable at every point in the interval. What this is saying is that when we go back to functions or limits or so, I think we've seen something like this. But if you don't recognize, I think you have to go back. Whenever we have an interval like this, let's see, I'm just using a and b, and I write this, right? And I write a, and I write this one. And when I write this, b, and let's say I do this, and I do this, and I do this. Each and every one of these are different. They are saying different things, right? So this actually square bracket here is just trying to say closed, right? This trying to say an open, right? So when you see open here, this one is closed here, open here, close here, right? So this one is saying say an open interval, meaning say whatever thing that we are doing, we don't usually include the a and then b. The a and b are just the boundaries. Are we okay? Adjust the boundaries of that interval. So if you don't remember that, I think you'll have to go back and then maybe refresh on that one. So what you're trying to say here is that if a function is differentiable on an interval a and b, then every point in that particular interval is differentiable at that point. So let's say I have a number line. Let's say, because we are doing real numbers, that's why I draw number lines at time. Let's say 1, 2, 3. Let's say like 1, like 2, like 3, right? And then let's say I write this interval this way. I'm having an interval. Let's say -2 and then 3. And I'm saying that the function is differentiable on this interval, meaning that at when I have the function, let's say f, and I put the 2 inside, the limit will exist, right? Or f on then this -2 on this negative on, and here is 3, the limit will exist. But then if it happens that I pick any value apart from -2 and then 3, anything between them, the function will be differentiable at those points. That's what I'm saying, because this is an open interval, and I'm saying that the function is differentiable on this interval, right? But if it happens that, let's say I have something of this sort, let's say close brackets, right, a square bracket, I have -2 here and then 3 here, meaning that every value, right, within this particular interval, the function is differentiable at that point, including -2 and 3, because what, this is a closed interval. A closed interval usually signifies that the boundaries are actually part of the interval, right? For the differentiation, it can be written in different ways. This way, this way. That's what this side means, right? But generally, we see these ones. And this one, most of the time, you see it to be this way, right? dy dx. And remember, I said this y here, because it's a function of the x, we at times write it this way, right? So you can even see it at the side. Yes, f of y here, right? But this actually, and this, sorry, this is f of x, and you see there's a y here, and here is f, right? So this one here too is the same as this one here. You see, yeah. Now we have to find the derivative of the function at this point. Now if we remember what we've done so far, we are saying said the derivative of a function at a particular point is like finding the limit at that point as the x is approaching that point.